we can continue later.
Yeah.
Okay, so it's now 15 past. So welcome everyone to this this week's machine learning coffee seminar. So we will now be having these sessions weekly on Mondays. And this week we have Assistant Professor Jarno Vanhatalo, who is an Assistant Professor of Statistics in University of Helsinki, and he's going to talk about some statistical inference on applied areas. So please, Jarno, go ahead.
Okay, thank you, and thank you for the introduction. I hope you can see my screen. Yes, and all right. So what I'm going to talk to you today is basically related to a kind of a longer project that I've been involved in, and the perspective I try to take here is basically the statistical inference, prediction, and data for ecological risk assessment in remote Arctic marine areas. And the motivation for this topic comes from the kind of it all is related to climate change in a sense. And basically what climate change is doing is it's warming up the polar areas, and kind of one positive consequence of that is that the shipping route from Asia, which is around here, is getting short. The shipping from Asia to Europe is coming shorter, so that there's a potential of using this northern sea routes, so that we can either ship material through this kind of a Russian water areas or from the Canadian areas. And what is the benefit from that is that it's much shorter than the current shipping routes, and then there are kind of the political reasons also, so that the kind of the parties involved are different in this northern area than in the southern routes. And what we can see already now is that the traffic has increased a lot, so that if we look at the distance traveled in this northeastern lane or route, it's been increasing in ice infested waters as well as in open waters, and the total distance traveled in those areas has been increasing quite a lot. And this picture here this comes from Arctical Ltd, and I think this is most likely a picture from Baltic Sea, but this is showing kind of the main way how these routes are used, so that we have icebreaker going in front of the convoy that is followed by various ships. And basically this is something that has two issues related to it. So there's a huge commercial potential for this route, but then there are also serious threats both to the environment, but then also to the local people and to the safety of the ship crew as well. And that was the main motivation for two consortia, the SeArctic consortium that was active from 2013 to 2018, and the Temporal consortium that is still active until the end of this year. And these are consortia that have been led actually from Aalto University and the School of Engineering, and my role there has been related to the environmental risk assessment related to potential oil spills. So that one of the biggest threats for the Arctic Sea environment posed by this kind of a increasing ship traffic is actually oil accident. So that if there is a ship accident, there's always oil leaking to the water, and that will have some effects on the Arctic biota. And basically what the situation currently is that there's very limited knowledge on both the Arctic ecosystems themselves, so that what do we actually have there and where are those key elements of the ecosystem. And then also related to the risks posed by this increasing traffic. And then that is actually the kind of the starting point for from where we started in 2013, so that we started to look at that. Okay, what can we actually say about those risks related to this marine traffic in Arctic seas? This brings us to the definition of risk and how probability is related to that. And basically, there are many ways to define risk and many approaches to actually study risk and mitigate it. But basically, all of those approaches and definitions, they have typically two separate kind of quantities there. There's the quantity of harm, so that we need to be able to somehow say that that if something goes wrong, what is the harm caused? And then there is some kind of notion of uncertainty or probability that this particular harm will realize. And now, if we take a Bayesian stance, what we can do is that we can actually define risk as the expected utility, or in this case, expected loss, so that we look at that, what is the expected loss given we choose some action. And then this function f here, this is the function that maps some of our model parameters, the environmental conditions, the location of action, and then the period of time when we are posing that action to those actual losses that we are interested in. And then this probability density function here, or probability distribution here, that's then the description of on the uncertainties related to those model parameters, environmental conditions, etc. And to give a concrete example that what this loss could be, so this could be, for example, the number of dead animals after choosing some route in the Northern Sea route. And here on the right, I have a map of Kara Sea, which is the case study area that I will be discussing during my talk. So this is the Novaya Zemlya. Finland is over here, somewhere down here, and then I have 5 different routes. So that what I'm assuming is that let's think about that we want to ship oil from Dixon to Barents Sea or to the Laptev Sea around here. And then the decision or action that we can choose could be that, okay, well, which of these routes should we take? And then from environmental consequences point of view, the loss could be that, okay, well, if we start shipping through one of these routes, what is the number of dead animals that arises through that action? That number can be 0, and the biggest probability for 0, biggest probability is actually typically for 0, because it is not that common to have those accidents, but still there's non-zero probability to have the accident through which some animals would die. And then we will be using models, and this theta here describes those model parameters, and then this x tilde s tilde t tilde, those will denote the environment along this route, as well as the spatial coordinates of these routes, and then also the time of operation, so that whether we are shipping in spring, summer, or fall, and which month we actually take. And in principle, we could then calculate the expected loss, so that the expected number of animals that will die if we decide to ship oil through one of these routes. But however, what I will argue at the end of my talk is that this expected loss is not the whole story. So actually, from risk management and assessment point of view, we actually want to know the whole probability distribution. And how to conceptualize this is something that we can actually conceptualize this as a directed acyclic graph, so that we start from parameters or variables that we can actually control. so that we can control, at least we can assume that we can control the type of oil that will be shipped. Then there are control measures for the spill size, so that that we can do some kind of ship design decisions, or we can for example say that what is the maximum amount of oil that can be shipped through a certain route. Then we can decide that what is the season when we are doing that trafficking, and then we can also choose the route which we will use for that. And after that, the actual risk assessment that has to be done is related to making some kind of inference or statement, probabilistic statements considering the environmental covariates in the area of operation. Then we need some understanding of the population distribution, or the numbers of animals or other biological entities that are in there. We need to know something about the area that will be oiled if accident happens. And then we need to know also the accident probability along the different routes. And based on this information, what can be said is that, okay, we can actually calculate the proportion of population in oiled area, which is mathematically denoted here, so that if there's an accident at location S, and then it leads to oil spill of size A, then basically this lambda here, this is a probabilistic description of the intensity of animals. But in this case, I'm talking about animals, but it could be something else also, like plant or invertebrates or so on. But then this here is the kind of a functional description of the intensity of those animals. And pictorially, what it means is that if we have an oil slick that is centered at S, and then we know that there are, for example, two species whose distribution and density, population density, is described by these blue and red colors. Then what can we say is that, okay, we can basically calculate that what proportion of that population is exposed to oil, and if the slick is bigger, then the proportion is bigger, and then we are more likely to expose also more populations. And that gives us one of the measures that we will be looking at is the proportion of population at risk, which is basically the amount of or the proportion that is within the oiled area if an accident happens. But then some species, they are more likely to actually get in contact with oil than others. And then if they get in contact, they might either die or stay alive, so that they are not affected that much. So that, for example, the young polar bears, they are more likely to get exposed. They are more likely to die if they get oiled, but they are less likely to get exposed than their mothers, for example. And then on the other hand, for example, walrus, it's not that likely that it will die even if it was exposed, because its fur is very different and skin is very different compared to polar bear. And now all these components here, they are basically spatial temporal functions which we don't know exactly. So we want to make some kind of statistical inference on them. And now the talk is pretty much kind of giving some understanding that how we did this. And basically, what we started with was kind of a massive open source intelligence project in a sense that we just started collecting all kinds of information that we thought would be important or informative on these things. So we went and we collected all the open source sea charts. Then we collected all sea ice concentration and ice properties from various places, so NASA, National Snow and Ice Data Center, etc. We even found some repositories which had annual measurements for monthly river discharges in this area, etc. And basically, some of these were easily available through internet, but some of them were such that we had to just order physical articles and physical books, and then we had to digitalize the information from them. And one example of those openly available and already digitized datasets were these sea surface temperature and sea surface salinity measurements from Karasi region. So these dots here, these show the measurement locations for this sea surface temperature and salinity in Karasi region. And then basically why we would be interested on these two parameters is basically that those are very good proxies for the basic production in the area. So that now what's happening, there are major rivers flowing water into the Karasi, which then decrease the salinity of the sea and also increase the temperature, but they also bring nutrients, which is then the basic driver for the basic production. And then, for example, walruses and seals, they will then follow this basic production, because then it typically means also more fish and mussels, etc. And basically, the model that we used to actually produce predictions for these two variables, so sea surface temperature and salinity, was quite simple spatial temporal model, where the kind of the one of those catches was this, that it was a very incoefficient model, so that our the weight for explanatory variables, so for example river discharge, which is here, that was assumed to affect the sea surface temperature differently in different parts of Karasi. And this figure here shows that what is the effect. So the river effect was positive on this kind of a western part of the Karasi, and then it was mostly negative in the northern part of the Karasi. And this was actually producing also nice kind of intermediate results that were interesting by themselves also, because there is not that much research on the published research from Karasi oceanography either. Then another thing that we needed, so now that we had some understanding about the environment and environmental conditions, then we had to build some understanding of that where are the species of interest. And now the end products are shown here, so that these are kind of summarizing the analysis for polar bears, seals, and walrus and seals, so that this is the relative intensity of those animals in different locations and in different seasons, so that in the case study area. And why this is interesting is that now we have some understanding that there are those vulnerable entities that we want to, for example, conserve, or we don't want to get affected. And what can be seen is that the patterns are quite different. So that, for example, polar bear and seals, they seem to be they don't seem to be in the area that much during the summer, whereas walrus are there over kind of the year round. So that this also has an effect on the risk assessment. And the data that we had here was basically that came from those physical books and articles. So that this is basically a scanned series of scanned maps, where these red lines, those are the transect lines, and then these dots are the sightings of those animals at different locations. And each map here represents different source of information, so that now that we built the model, kind of the simple thing was that we had a negative binomial model for the animal counts, which had some spatial temporal description for the log intensity, and then we had some random effects for the observation processes. And this is, so statistically speaking, quite simple, but it was quite a big effort actually to acquire the data. But then what is interesting when working with these kind of data is that they typically are not that accurate and then reliable. And now, even though negative binomial is claimed to be a rather robust model compared to Poisson model, for example, it actually turns out that it is not that robust after all, because it is still it still belongs to the exponential distribution family. And it can be shown that exponential distribution family is not robust in a sense what is typically defined to be a robust model in Bayesian analysis. And kind of one clear example is that this is one scenario prediction for one for kind of that how the prediction of polar bear relative density changes when we have the original data, which contained one kind of a big outlier there. So the original data, when we talk in terms of n, that had in approximately 10,000 ice concentration measurements, where we had the sighting of either whether we have polar bears or not. And there was single observation out of those 10,000 where we had reportedly 0 ice concentration and 2 polar bears, and it affected the intensity prediction. So this is the mean prediction, so that it increased the intensity prediction over 2-fold compared to that we leave that sighting away. And the reason why that was erroneous was that the satellite images, they are not just too accurate near shore. And for example, this particular picture was such that instead of 0 ice, there was actually almost 100% ice when we double checked it. So this is kind of a reminder that what are the dangers of just blindly using data from open sources. Then something that we don't have data at all is this are these estimates of the sensitivity of animals to oil and their kind of the likelihood of them to actually get exposed by oil if they are within the oiled area. So now if we think about the different animals, they might be actually located in the area where oil comes, but they might either dive under the oil so that they get never exposed, or they for example dive through the oil when they get exposed. And then there's a huge difference that whether they will die or not after exposing to it. And this was something that luckily we don't have any observations for these 3 species. So this was something that we had to rely on expert opinion, so that we had to do expert elicitation to get some kind of probability distributions, that what is the proportion of population that would get exposed to oil if in oiled area, and what is then the probability, what is then the proportion of population that would die if they get exposed. Then a few other components, spreading of oil. I will jump over this quite fast, but this was something that, again, no reliable estimates from previous or any observations, because luckily we haven't had any accidents yet. And then basically what we ended up doing was that we built a quite simple spreading model for oil, so that we get some estimate that what is the area covered by spilled oil as a function of the ice concentration and then the spill size. Then something that was again, massive open source intelligent project was to estimate the accident probability. So, and this was actually something that we were able to get kind of a database estimate, so that there are openly or semi-openly accessible data repositories that have information that on types of vessels and their routes. So it's the so-called AIS data. But what is, and then we have some vessel databases that actually contain information on the technical details of those vessels. And this was, again, from a statistical point of view, this was really simple analysis, so that we just applied Bayesian regression model with exponential distribution for distance between accident events. But the kind of the tricky part here was to actually find the data and then extract the data efficiently, so that we and then also to check the quality of the data, so that we don't have erroneous data points there. But what we were able to do was basically that we were able to produce probably predictive distributions for the numbers of besetting events. So that was the type of accident that we were interested in. So besetting means that that a ship gets stuck in ice, which then can cause serious trouble if the ice starts to push the ship, for example, to shallow areas, which leads to grounding or something like that. And there are differences, significant differences between different ice categories. So category A is the best category, and category C is the worst category. And then we can see that there's very big differences in the probability of besetting event or accident between different seasons, but also between different locations, which varies according to the environmental conditions. Okay, so after doing all these estimates, what can we do finally is that now we can start propagating the uncertainty through this DAG, so that we have some probability models for environmental coverage, population distribution, etc. And now we can start looking at that. What is the expected proportion of population at risk? So this would be the proportion of a Kara-Sea population that is within the oiled area if there's an accident at a particular location along a different route. And then we can also look at the expected oil spill impact, which is then basically what is the proportion of population that would die if there's an accident. And here, this figure is now summarizing some of the results, so that how to read this is that now the first 4 box plots here, those are now corresponding to this proportion of population at risk with different levels of accuracy in the uncertainty estimation. So that the first 2 are that we don't include any uncertainty estimates, so that those would correspond to kind of a maximum a posteriori estimates for the model parameters and seasonal means for the environmental coverage. Then we start adding uncertainty estimates for the model parameters, and then also to the environment. And then this final here, final box plot, this is including all the uncertainty sources, and then also the effect, kind of the effect that not all individuals get affected by the oil. And what is kind of the key message here? So there are many box plots, but kind of the key message to mention here is that actually kind of increasing the model realism, it increases the uncertainties, but it can actually change the expected results very drastically, so that we can have also very big differences in the expected values in addition to those wider uncertainty estimates. Then what we are working currently, so this is now work in progress slide, is that now we are looking a little bit more in detail, so that now here what I have drawn is basically the probability distribution along different routes for this proportion of population at risk on different seasons or on different months, and then for over one season. So this black curve here is the risk for spring, and then these red and blue curves, they are now the risk for one particular month during the study period. And what can be seen is that there's considerable uncertainty in the monthly predictions, but even larger predictive uncertainty when we take into account that we look at the seasonal prediction when the environmental conditions are uncertain. And then this is the similar figure over the route, and here this is the so-called uncertainty partition, which is basically summarized in terms of variances. So that what is the relative contribution from kind of uncertainty in model parameters, and then in the environmental variability. And what is seen from here is that it might differ a lot depending on the different species. So that for some species, it's actually the environmental uncertainty that is driving most of the uncertainty there. And for some other species, it's actually the model uncertainty. Okay, I will jump over this because I'm quite short of time already, so that I come to the discussion and conclusions. So basically, what this exercise has been is that we have wanted to provide first ever quantitative estimates for the environmental risks posed by Arctic ship traffic, and this is all the results are now for acute effect, so that what's going to happen right or immediately after an accident, if such happened. And that currently it's unfeasible to provide any quantitative estimates for long-term effects for that region. So we just don't have enough information so that we could provide anything quantitative. Some take-home messages for this audience, I think, is that what's interesting from statistics and kind of a machine learning point of view is that now there are actually quite a lot open access data also from remote areas. But what is something to note is that this big data does not necessarily contain big information. So we might have a gigabytes or terabytes of ice concentration measurements, for example. But actually, it's very hard to turn that information into useful risk assessment estimates. And then there's a clear need for robust models for count unknown other non-Gaussian data, so that when we start relying on these remote sensed kind of data sets, at least in my experience, they often contain very big errors occasionally, which can actually cause significant kind of alterations to your model inference if you're using non-robust models. But what is interesting from my point of view is that the robust models, they are mostly studied for Gaussian data, but there aren't good robust models for Poisson or binomial data, for example. So that's a clear deficiency. Then model assessment and comparison methods. That's something that, as you can see, everything was based on the model predictions. So now the crucial question is that, are our models good? And are those uncertainty assessments good? So this is something that I would say that for example, in Aalto, there are many people who could have something to say on that. Good. I jump to my last slide, which is thanks to collaborators and the team and a few of the references that I mentioned during my talk.
Okay, thanks, Jarno, for the very interesting talk. So if you have any questions, then you can write them in the chat or just ask ahead. So we have already a few questions. So during the talk, Anna asked that were all data sources open, or did you use some proprietary data?
Yeah, so all data was open access in a sense that it was we could either find it from open source repositories, or that we could buy it in a sense that we buy a scientific journal article or so. But then something to notice is also, which I forgot to mention, is that many of that data was published in Russian, and we didn't have any Russians, anyone who would speak fluent Russian in our team. But we had one really smart trainee from Germany, Anja Wilken, who was really good at using Google Translator and other machine learning applications for translating things. So she was basically translating pages from books and articles written in Russia, and we are actually quite confident that she did a really good job in the terms that we are confident that we were able to actually understand those material without having a Russian speaker in our team.
Okay, thanks. And then Antti Honkala wrote a question in the chat asking or saying that your results seem to have a long tail towards high risk. Do you think the current methods are sufficient for analyzing this? If not, what else would be needed?
Yeah, that's a very good question, and I think we are. Yeah, let's put it this way, so that I would say that we are very far from the level of trustworthiness compared to, for example, nuclear safety assessments or something like that. So these are, I would emphasize that these are the first quantitative risk assessments that include kind of a proper quantification of uncertainty. And I would say that these are still qualitative in a sense that we shouldn't take these results as kind of a definite kind of statements that what is the actual uncertainty and what is the actual probability for certain consequence. But I would say that these provide good probably quite good understanding of the scale of the uncertainties and the relative importance of those different uncertainty sources. And what is very typical to Arctic environment and environmental risks in more general is that the tails are really long and heavy typically. So that if we think about now, for example, walrus, it's a species that tends to form big kind of herds, so that we might have something like 5,000 walruses in one place that is suitable for them, and then another place which would be equally suitable for walrus. They just happen to be absent. And the same goes for different birds, so that the tails are very thick, and that's kind of the property of the problem. But then whether these tails, for example, this one that I jumped over, whether we should trust that the tail ends at 300 or whether it should be 1,000, that's then a different matter.
Okay, Maria has a question. Are the oil shipping companies operating on Arctic regions considering these or similar results when planning their routes?
To my knowledge, no. So, and this this is one of the reasons why Lloyd's Register Foundation actually was interested on funding this project. Is that so Lloyd's Register is one of the biggest registering companies for shipping that kind of gives the certificates for shipping companies, and their foundation it's funding many things. So it's funding, for example, Alan Turing Institute, etc. But they were interested on our project specifically, or consortium, because we were actually addressing the questions that they think shipping companies should be addressing as well. And then kind of a anecdote related to this question. So the reason why we are trying to give some kind of quantitative assessments for the actual numbers of animals that die. So from ecological point of view, it's actually more important to look at the relative proportion, or the proportion of population that is affected. But then from a shipping company point of view, it is actually more important to look at the actual numbers. Because if you think about the public reputation and what is the effect of accident to that, it is directly related to the number of polar bears that get smothered by oil, for example. And this is something that some people in our consortia did look at, and it was actually quite interesting to notice that, for example, Shell and Exxon, if I remember right, that who they interviewed, they were actually really concerned about this, so that they didn't think about it so much from the ecological perspective, but they look at it from the public perspective, or the kind of the public reputation perspective. So that if someone can say that it's non-negligible probability that they will kind of kill certain amount of polar bears or seals if their ship grounds, then that most likely has some effect on their decisions.
Okay, and then Carlos has a question. Great comment now about what are the incentives for which governance actors, or this may be more of a comment.
Yeah, no, just a comment, but an interesting point that if we try to do this with people, if we try to assess the risk of something happening in Helsinki, for example, which we are actually looking at, then it becomes very difficult maybe to talk about, you know, should we model the people who are going to die, or is that maybe a no-no, and maybe something else will be a better driver for changing policies, or just a comment.
Yeah. Yes, and then the risk perspective is very different for different people. So that it's that is something to note as well.
Okay, we still have a few minutes. Any comments or more questions? You can just directly ask if you want.
I'm curious to know what's the budget for this consortium and the amount of people involved into this kind of project that you have presented.
I probably should remember this by heart, but I think it was the full kind of the both of the consortia. I think it was something between 3 and 4 million pounds. But it should be remembered that this was only one part of the project. So really significant amount of this consortia was actually the ship engineering part, which is basically looking at the kind of the ship structure, the logistical questions, etc. And that took more than half of the project budget. So that there were many collaborators in this, and most of those, for example, the German and Memorial and NTNU and Aalto, they all had at least some of their team looking at this kind of a ship construction and questions related to that. But then how many people? So for example, this project has taking all the different subfields. We have produced approximately 15 PhD theses, etc. So this has been really big consortium.
Mm-hmm.
And from my from this project that I'm presenting here, this has produced kind of a little bit depending on how to count those and allocate those, but 3 or 4 PhDs, and then 1 postdoc has been working actively on this.
Right, thank you.
Okay, so we are now out of time. So I would like to thank the speaker, Jarno, again for a really interesting talk, and also the audience for your attention and lively discussion. So we will meet next week again, and next week we will have Alex Young talking about big data over network settings. Okay, so thanks a lot for everyone, and have a nice day. Goodbye.